David Hilbert was a German mathematician. He is recognized as one of the most influential and universal mathematicians of the 19th and early 20th centuries. Hilbert discovered and developed a broad range of fundamental ideas in many areas, including invariant theory and the axiomatization of geometry. He also formulated the theory of Hilbert spaces, one of the foundations of functional analysis. Hilbert adopted and warmly defended Georg Cantor's set theory and transfinite numbers. A famous example of his leadership in mathematics is his 1900 presentation of a collection of problems that set the course for much of the mathematical research of the 20th century. Hilbert and his students contributed significantly to establishing rigor and developed important tools used in modern mathematical physics. Hilbert is known as one of the founders of proof theory and mathematical logic, as well as for being among the first to distinguish between mathematics and metamathematics. Early life and education. Hilbert, the first of two children of Otto and Maria Therese Hilbert, was born in the province of Prussia, Kingdom of Prussia, either in Königsberg or in Wellor near Königsberg, where his father worked at the time of his birth. In late 1872, Hilbert entered the Friedrichs-College Gymnasium, but, after an unhappy period, he transferred to and graduated from the more science-oriented Wilhelm Gymnasium. Upon graduation, in autumn 1880, Hilbert enrolled at the University of Königsberg, the Albertina. In early 1882, Hermann Minkowski returned to Königsberg and entered the university. Hilbert knew his luck when he saw it. In spite of his father's disapproval, he soon became friends with the shy, gifted Minkowski. Career. In 1884, Adolf Hurwitz arrived from Göttingen as an extraordinarius. An intense and fruitful scientific exchange among the three began, and Minkowski and Hilbert especially would exercise a reciprocal influence over each other at various times in their scientific careers. Hilbert obtained his doctorate in 1885, with a dissertation written under Ferdinand von Lindemann, titled Über invariant Eigenschaften spezieller binärer Formen, insbesondere der Kugelfunktionen. Hilbert remained at the University of Königsberg as a private docent from 1886 to 1895. In 1895, as a result of intervention on his behalf by Felix Klein, he obtained the position of professor of mathematics at the University of Göttingen. During the Klein and Hilbert years, Göttingen became the preeminent institution in the mathematical world. He remained there for the rest of his life. The Göttingen school. Among Hilbert's students were Hermann Weyl, chess champion Emanuel Lasker, Ernst Zermelo, and Carl Gustav Hempel. John von Neumann was his assistant. At the University of Göttingen, Hilbert was surrounded by a social circle of some of the most important mathematicians of the 20th century, such as Emmy Noether and Alonzo Church. Among his 69 Ph.D. students in Göttingen were many who later became famous mathematicians, including Otto Blumenthal, Felix Bernstein, Hermann Weyl, Richard Courant, Erich Keck, Hugo Steinhaus, and Wilhelm Ackermann. Between 1902 and 1939, Hilbert was editor of the Mathematische, the leading mathematical journal of the time. He did not have enough imagination to become a mathematician. Hilbert's response upon hearing that one of his students had dropped out to study poetry. Later years. Hilbert lived to see the Nazis purge many of the prominent faculty members at University of Göttingen in 1933. Those forced out included Hermann Weyl, Emmy Noether, and Edmund Landau. One who had to leave Germany, Paul Bernays, had collaborated with Hilbert in mathematical logic, and co-authored with him the important book, Grundlagen der Mathematik. This was a sequel to the Hilbert-Ackermann book Principles of Mathematical Logic from 1928. Hermann Weyl's successor was Helmut Hesse. About a year later, Hilbert attended a banquet and was seated next to the new Minister of Education, Bernhard Rust. Rust asked whether the Mathematical Institute really suffered so much because of the departure of the Jews. Hilbert replied, "Suffered? It doesn't exist any longer, does it?" By the time Hilbert died in 1943, the Nazis had nearly completely restaffed the university, as many of the former faculty had either been Jewish or married to Jews. Hilbert's funeral was attended by fewer than a dozen people, only two of whom were fellow academics, among them Arnold Sommerfeld, a theoretical physicist and also a native of Königsberg. News of his death only became known to the wider world 6 months after he had died. Hilbert was baptized and raised in the Reformed Protestant Church. He later on left the church and became an agnostic. He also argued that mathematical truth was independent of the existence of God or other a priori assumptions. The epitaph on his tombstone in Göttingen consists of the famous lines he spoke at the conclusion of his retirement address to the Society of German Scientists and Physicians on 8 September 1930. The words were given in response to the Latin maxim, ignoramus e ignorabimus, or, we do not know, we shall not know. Wir müssen wissen. Wir werden wissen. In English, we must know, we will know. The day before Hilbert pronounced these phrases at the 1930 annual meeting of the Society of German Scientists and Physicians, Kurt Gödel, in a roundtable discussion during the Conference on Epistemology held jointly with the Society meetings, tentatively announced the first expression of his incompleteness theorem. Personal life. In 1892, Hilbert married Kathy Gerisch, the daughter of a Königsberg merchant, an outspoken young lady with an independence of mind that matched his own. While at Königsberg they had their one child, Franz Hilbert. Hilbert's son Franz suffered throughout his life from an undiagnosed mental illness. His inferior intellect was a terrible disappointment to his father, and this misfortune was a matter of distress to the mathematicians and students at Göttingen. Minkowski, Hilbert's best and truest friend, died prematurely of a ruptured appendix in 1909. Hilbert solved Gordon's problem. Hilbert's first work on invariant functions led him to the demonstration in 1888 of his famous finiteness theorem. 20 years earlier, Paul Gordon had demonstrated the theorem of the finiteness of generators for binary forms using a complex computational approach. Attempts to generalize his method to functions with more than 2 variables failed because of the enormous difficulty of the calculations involved. In order to solve what had become known in some circles as Gordon's problem, Hilbert realized that it was necessary to take a completely different path. As a result, he demonstrated Hilbert's basis theorem, showing the existence of a finite set of generators for the invariance of quantics in any number of variables, but in an abstract form. That is, while demonstrating the existence of such a set, it was not a constructive proof. It did not display an object, but rather, it was an existence proof and relied on use of the law of excluded middle in an infinite extension. Hilbert sent his results to the mathematician. Gordon, the house expert on the theory of invariance for the mathematician, could not appreciate the revolutionary nature of Hilbert's theorem and rejected the article, criticizing the exposition because it was insufficiently comprehensive. His comment was, "Das ist nicht Mathematik, das ist Theologie." Klein, on the other hand, recognized the importance of the work, and guaranteed that it would be published without any alterations. Encouraged by Klein, Hilbert extended his method in a second article, providing estimations on the maximum degree of the minimum set of generators, and he sent it once more to the Annalen. After having read the manuscript, Klein wrote to him, saying, "Without doubt this is the most important work on general algebra that the Annalen has ever published." Later, after the usefulness of Hilbert's method was universally recognized, Gordon himself would say, "I have convinced myself that even theology has its merits. For all his successes, the nature of his proofs stirred up more trouble than Hilbert could have imagined at the time. Although Kronecker had conceded, Hilbert would later respond to others' similar criticisms that many different constructions are subsumed under one fundamental idea. In other words, through a proof of existence, Hilbert had been able to obtain the construction. The proof was the object. Not all were convinced. While Kronecker would die soon afterwards, his constructivist philosophy would continue with the young Brouwer and his developing intuitionist school, much to Hilbert's torment in his later years. Indeed, Hilbert would lose his gifted pupil, Weil, to intuitionism. Hilbert was disturbed by his former student's fascination with the ideas of Brouwer, which aroused in Hilbert the memory of Kronecker. Brouwer, the intuitionist in particular, opposed the use of the law of excluded middle over infinite sets. Hilbert would respond, taking the principle of the excluded middle from the mathematician is the same as prohibiting the boxer the use of his fists. Axiomatization of Geometry. The text Grundlagen der Geometrie, published by Hilbert in 1899, proposes a formula set, called Hilbert's axioms. Substituting for the traditional axioms of Euclid, they avoid weaknesses identified in those of Euclid, whose works at the time were still used textbook fashion. It is difficult to specify the axioms used by Hilbert without referring to the publication history of the Grundlagen, since Hilbert changed and modified them several times. The original monograph was quickly followed by a French translation, in which Hilbert added ʻvɪt, the completeness axiom. An English translation, authorized by Hilbert, was made by E.J. Townsend and copyrighted in 1902. This translation incorporated the changes made in the French translation, and so is considered to be a translation of the second edition. Hilbert continued to make changes in the text, and several editions appeared in German. The seventh edition was the last to appear in Hilbert's lifetime. New editions followed the seventh, but the main text was essentially not revised. Hilbert's approach signaled the shift to the modern axiomatic method. In this, Hilbert was anticipated by Moritz Pasch's work from 1882. Axioms are not taken as self-evident truths. The elements, such as point, line, plane, and others, could be substituted, as Hilbert is reported to have said to Schoenflies and Cotter, by tables, chairs, glasses of beer and other such objects. It is their defined relationships that are discussed. Hilbert first enumerates the undefined concepts: point, line, plane, lying on, betweenness, congruence of pairs of points, and congruence of angles. The axioms unify both the plane geometry and solid geometry of Euclid in a single system. The 23 problems. Hilbert put forth a most influential list of 23 unsolved problems at the International Congress of Mathematicians in Paris in 1900. After reworking the foundations of classical geometry, Hilbert could have extrapolated to the rest of mathematics. His approach differed, however, from the later, foundationalist Russell Whitehead or encyclopedist Nicholas Bourbaki, and from his contemporary Giuseppe Pino. The mathematical community as a whole could enlist in problems, which he had identified as crucial aspects of the areas of mathematics he took to be key. The problem set was launched as a talk, The Problems of Mathematics, presented during the course of the Second International Congress of Mathematicians held in Paris. The introduction of the speech that Hilbert gave said, "Who among us would not be happy to lift the veil behind which is hidden the future, to gaze at the coming developments of our science and at the secrets of its development in the centuries to come? What will be the ends toward which the spirit of future generations of mathematicians will tend? What methods, what new facts will the new century reveal in the vast and rich field of mathematical thought?" He presented fewer than half the problems of the Congress, which were published in the Acts of the Congress. In a subsequent publication, he extended the panorama, and arrived at the formulation of the now canonical 23 problems of Hilbert. The full text is important, since the exegesis of the questions still can be a matter of inevitable debate. Whenever it is asked how many have been solved, some of these were solved within a short time. Others have been discussed throughout the 20th century, with a few now taken to be unsuitably open-ended to come to closure. Some even continue to this day to remain a challenge for mathematicians. Formalism. In an account that had become standard by the mid-century, Hilbert's problem set was also a kind of manifesto that opened the way for the development of the formalist school, one of three major schools of mathematics of the 20th century. According to the formalist, mathematics is manipulation of symbols according to agreed-upon formal rules. It is therefore an autonomous activity of thought. There is, however, room to doubt whether Hilbert's own views were simplistically formalist in this sense. Hilbert's program in 1920, he proposed explicitly a research project that became known as Hilbert's program. He wanted mathematics to be formulated on a solid and complete logical foundation. He believed that in principle this could be done by showing that all of mathematics follows from a correctly chosen finite system of axioms, and that some such axiom system is provably consistent through some means such as the epsilon calculus. He seems to have had both technical and philosophical reasons for formulating this proposal. It affirmed his dislike of what had become known as the ignorabimus, still an active issue in his time in German thought, and traced back in that formulation to Émile Dubois-Reymond. This program is still recognizable in the most popular philosophy of mathematics, where it is usually called formalism. For example, the Bourbaki group adopted a watered-down and selective version of it as adequate to the requirements of their twin projects of writing encyclopedic, foundational works, and supporting the axiomatic method as a research tool. This approach has been successful and influential in relation with Hilbert's work in algebra and functional analysis, but has failed to engage in the same way with his interests in physics and logic. Hilbert wrote in 1919, "We are not speaking here of arbitrariness in any sense. Mathematics is not like a game whose tasks are determined by arbitrarily stipulated rules. Rather, it is a conceptual system possessing internal necessity that can only be so and by no means otherwise." Hilbert published his views on the foundations of mathematics in the two-volume work Grundlagen der Mathematik. Gödel's work Hilbert and the mathematicians who worked with him in his enterprise were committed to the project. His attempt to support axiomatized mathematics with definitive principles, which could banish theoretical uncertainties, ended in failure. Gödel demonstrated that any non-contradictory formal system, which was comprehensive enough to include at least arithmetic, cannot demonstrate its completeness by way of its own axioms. In 1931 his incompleteness theorem showed that Hilbert's grand plan was impossible as stated. The second point cannot in any reasonable way be combined with the first point, as long as the axiom system is genuinely finitary. Nevertheless, the subsequent achievements of proof theory at the very least clarified consistency as it relates to theories of central concern to mathematicians. Hilbert's work had started logic on this course of clarification. The need to understand Gödel's work then led to the development of recursion theory, and then mathematical logic as an autonomous discipline in the 1930s. The basis for later theoretical computer science, in Alonzo Church and Alan Turing, also grew directly out of this debate. Functional analysis. Around 1909, Hilbert dedicated himself to the study of differential and integral equations. His work had direct consequences for important parts of modern functional analysis. In order to carry out these studies, Hilbert introduced the concept of an infinite-dimensional Euclidean space, later called Hilbert space. His work in this part of analysis provided the basis for important contributions to the mathematics of physics in the next 2 decades, though from an unanticipated direction. Later on, Stefan Banach amplified the concept, defining Banach spaces. Hilbert spaces are an important class of objects in the area of functional analysis, particularly of the spectral theory of self-adjoint linear operators, that grew up around it during the 20th century.